Okay, so hello everyone. This is Renqian and Yinse Xia from Microsoft Research to give this talk on BioGPT, a generative pre-trained transformer for biomedical text generation and mining. I am Renqian, the first speaker of this talk, and Yinse will give the rest part of the talk later. So in this talk, what we did is a GPT model trained on biomedical literature to assist the AI for science research, as the name tells us, and we call it BioGPT, where bio stands for the biomedical. So why do we need this BioGPT? We know that there are numerical documents, mainly the research papers in the web. For example, PubMed, PMC, Semantic Scholar, and Archive, many sources. They contain more than millions of research papers in the web, and they are keeping daily updated with more coming papers. So it is essential for a researcher to mining knowledge and information from those numerical papers, but it is impossible for one to go through or read all the paper or documents or the literature. It is impossible for a human to do so. So it requires an automatic tool to process the text for researchers to mine uh, the information and the knowledge behind those research papers. So previously, what we have for this purpose is some pre-trained language models for the biomedicine and life sciences domain are proposed. For example, the general purpose BERT and BioBERT, BlueBERT, or PubMedBERT, ScienceBERT, and ElectroMedBERT. All these models are based on the transformer encoder models that we call BERT, and they are pre-trained on massive general domain data and continue pre-trained on biodomain or directly pre-trained on the bio or science domain. These are those advantages, but also they have some disadvantages. Regardless of this, all these models are based on BERT models, which are better for understanding tasks, where they take the sentence as the input and output embedding of the words, and then do some tasks like classification or predicting. Um, so why do we need GPT for this task? Because GPT, we know that this is a very popular term in the recent days. GPT has shown powerful generative ability, which it can generative new text or new knowledge or some amazing text or amazing content from the knowledge it has learned, and it is a well-built multitask learner where it can be used for various downstream tasks like information extraction, text generation, and also the traditional classification. Also, it's a good few-shot learner where we just provide it with several few examples, and it can do well on the new data samples during the inference. Even if the model is powerful enough, it can do zero shot task where we do not give any example for the model to learn or to learn or to train. It can directly generalize well to the unseen new task and the data. So this is why we focus on GPT rather than the BERT model. So in our work, what we finally what we finally give is we export two models, our BioGPT and the BioGPT large version. Both two models are based on transformer decoder models, and that is the GPT model. The difference between two models mainly is the different sizes. BioGPT is a 24-layer transformer decoder model with 345 million parameters, which is trained on 30 million PubMed abstracts that is approximately 4 billion tokens. And the large version, a large model is 48-layer transformer decoder only model with 1.57 billion parameters trained on additional 6 million PMC full paper datasets with approximately 8 billion tokens. That is as twice as the previous one. So we also apply some additional techniques to the training and the data. For example, what we want to mention that since the research paper is different from general text, that research paper are always well organized in structured because they have very clear structure with title, abstract, introduction, methods, experiments, and conclusion. So the structure information is also important for the model to learn the relation between each part. So we carefully deal with the structure information. We add special tokens surrounding the different parts to let the model better learn this parts. So after the model is pre-trained, how do we apply it to multiple downstream tasks? Here, we adopt the prompt-based fine-tuning technology for downstream tasks. Here is the illustration of our framework on prompt-based fine-tuning. During fine-tuning, we just convert the downstream task to a sequence-to-sequence format where we use hard prompt or soft prompt to concat the input and the target to a whole natural language sentence, as shown here. And then we use the pre-trained BioGPT model to fine-tune on this whole sentence. And after fine-tuning, we can do inference with this fine-tuned model by inputted the source text and the prompt we have provided, and then the model is able to generalize to generate the answer. Mm, so we evaluated our models on several tasks, including relation extraction, question answering, and document classification. All this on biomedical domain. We mainly focus on drug-target interaction, chemical disease relation, and drug-drug interaction in relation extraction, and the PubMedQA dataset in question answering and the HOC in document classification across 6 data sets. So what's the results? Here we can see that our model achieved better than all previous methods, up to 4 points improvements in the relation extraction data task across all the 3 data sets. And our model achieved human parity on the PubMedQA task. On document classification, our model also achieves 3.28 improvement over previous model. So this is here we provide some examples of our model when fine-tuned on downstream tasks. Here is an example of drug target interaction extraction task, where the task is that when given a paragraph or some text, the goal is to find the triplet of drug, target, and the interaction between them in the document. Here is an example. The left part on the screen is an abstract from PubMed, and the right part, we inputted the paragraph into our BioGPT model, and it generates the output saying that the interaction between this red drug and the blue target is the inhibitor, indicating the interaction between those 2 items. And we can easily parse out the structure output of the triplet. And here is another example of drug-drug interaction extraction. So similar to the previous one, the task is to find the drug-drug interaction triplets in the document. We also provide a document with several sentences describing some interaction between 2 drugs. So after proceeding it to the BioGPT, it generates the sentence saying that the interaction between this red drug and this blue drug is a mechanism indicating their interaction. So when as it's a generative model, it is easy for it to continue generate if it detects more than one triplet in the document. So it continues to generate another sentence indicating another triplet of drug-drug interaction. And also we can easily parse out the structure output here. This is an example on question answering. This is data sample we get from the PubMedQA data set. So the question is listed here, is shown here, and the context. We combine the question and the context to the model. So the ground truth answer of this is yes, and our model, after producing the input, also generates the correct answer, with the answer to the question given the context is yes. So this is the case on question answering. All these three examples we shown here are based on fine-tuning technology, that we have to provide several examples for the model to fine-tune or to continue learn on. Might be cost of some resources, but we know that if the model, especially the GPT model, if it is powerful enough, or if it is powerful, it can do some zero-shot learning. That, as I just mentioned before, you don't have to provide data set for it to train, but it can directly infer on your task and on your data. So here we also test the zero-shot learning ability of our pre-trained BioGPT. This is also an example of question answering we get from the PubMedQA task. So we still get the question and the context. We concat them together to be a sentence, and we input to the model directly and ask the BioGPT to generate. So um, the ground truth answer to this question is no. And what we see from BioGPT is that it generates, the answer is that the SLBM is not a good alternative to SIP for measuring pupil size. So BioGPT correctly generates the answer for this question given the context. Uh, Remember that this is not this sentence the BioGPT generates is not in the format that is same to the previous one, since this is not fine-tuned at all. This is just the pre-trained version of our BioGPT. We here just test the zero-shot learning ability of the model, and it shows good ability on zero-shot learning. So what's more, we all as a generative model, we also would like to see the free text generation ability of the model. So here we provide some keywords of interest to the model and see how it generates. Um, and also we compare it to the GPT-2 standard model, where here we make a comparison too. So when we input some common words, both models can generate well on the words. But if we input some less common or uncommon words, that is in the biomedical domain, um, the both models become different. So for BioGPT, it still generates well on these two items, describing the items, what they are and what's the usage of those two items. But for GPT-2, it becomes it became to generate some incorrect answer or irrelevant answer. For example, for the second term, the GPT-2 takes it as the name of some city. So this is not true. Well, what's more is that if the item is contains more like capital letters and numbers, that is more like a code name of some some chemical or some drug or some disease or gene, um, or some other matter. The GPT-2 model will just maybe fail to generate well on this item. Like the first example, GPT-2 just begin count numbers, and in the second example, GPT-2 just takes it as some file name and generates some file or link. So in these two examples, BioGPT, our model still can generate a well-described sentence. We also input some keywords of interest that are popular, still are of interest now. We input COVID-19 and the virus SARS-CoV-2 into the model. Unfortunately, GPT-2 maybe lack of data, but it generates it takes the input as some um, as some like code names or whatever, just output some link or file name. It does not know what this is, but BioGPT can generate some good representation for this these two words. Also, we input some more words of interest. We test we input the treatment of COVID-19 and the drug that can treat COVID-19. Yes, so GPT-2 can generate some words, some sentence that are complete but have none but are not that but making no sense. While BioGPT can make a good conclusion of the words. So this is the part of BioGPT. Next, I will give it over to Yingce, and he will describe our BioGPT-2 model. So Yingce, now it's your turn.
Okay, thank you, Renqian, for the nice introduction. Hi, everyone. This is Inter from Microsoft Research AI for Science. I will present the second part. After proposing BioGPT, now we extend it to another version, BioGPT 2. The motivation is that in medical or healthcare literature, multiple types of entities appear together, like the text, the drug, the disease, and so on. They are deeply fused in the literature. Let us see an example here. This is from a paper about artemisinin. The drug artemisinin appears with the text together. The drug can be described not only by the drug names, but also by the drug molecular graphs. The text and the graphs are complementary to each other and they carry different information. So why not put them together to get a better model? By this motivation, we extend BioGPT to BioGPT-2, which is trained on both text and drugs. Next page. Yes, this is the model architecture of BioGPT-2. It is an 84-layer transformer model with about 1.5 billion parameters. The model is trained on 30 million PubMed abstracts, on 30 million smiles from PubChem, and also 8 million pseudo-parallel text smiles parallel data. For smiles, it is a sequential representation of the molecular graphs, which is obtained by traversing the molecular graph using depth-first search and some branching rules. Next page. Okay, let's see several examples here. The input, for the first example, the input is a disease and the output is a drug. And here the example is that generate a drug for HIV, where HIV is the disease. And we show three cases here, where our model generates several types, several candidates, and the three are all drugs for the HIV. Next one. For the second example, the input is a bit more complex, which covers both the disease and the target name. Here, the disease is the lung cancer, and the target is the EGFR. And we can also obtain several candidates, and they are all drugs for lung cancer, and they could all target an EGFR. And this shows the effectiveness of our method. Next page. This is the third example, where the input is the description of the virus, and the output is the candidate compounds. In this example, the input is the description of varicella, zoster virus, and the disease name does not appear in the description. Fortunately, our BioGPT tool successfully recovers the drugs that for this disease that can be used for the treatment for this disease. Next one. Okay, this is the summary of this lecture. First, we propose BioGPT, which is a strong generative model for biomedical domain, and it can be used for information extraction, text generation, and question answering. After that, we extend BioGPT to BioGPT 2, which enables the text-to-drug generation. And the code has been released in GitHub, and you can also find our model at the Hugging Face. Next one. Okay, this is the last page. Thank you for your listening, and we are looking forward to your feedback, suggestions, and comments. Feel free to contact us. Thank you.